So, oxidation and reduction is all about charge. As a friendly reminder, there are two mnemonics that you can use, or acronyms. The first is oil rig. I personally prefer Leo goes Gur, but take your pick that tell you whether this is an oxidation or reduction reaction. Oil rig oxidation is loss, reduction is gain. Or Leo goes Gur, loss of electrons is oxidation, gain of electrons is reduction. So whenever I'm asked about oxidation or reduction, the first thing I look at is which compound, which element seems to have had the greatest change from positive to negative. And because it's an oxidation reaction, there are some things we can just throw out. Any OHs or Hs are almost universally thrown out. So that's probably not this. And it's probably not the water. The second thing I start looking for is the metal. Where is the metal in this compound? Metals are the most commonly oxidized and reduced things. For instance, we could talk about the oxidation of zinc, where it loses 2 electrons and goes to zinc 2+. Notice how it goes from a no positive charge to a larger positive charge. What we're looking for in this case, this is an oxidation, a reduction would be something like Cu plus an electron goes to Cu. Notice how the positive charge got smaller. So let's look at the metals. And thankfully, or fortunately, in this particular setup, there's only one metal. Again, good place to look. It's here and here. So this goes from MnO4 to Mn2+. The question is, what's the original charge on the manganese? Well, what we have here is we have manganese and 4 oxygens. Each oxygen has a -2 charge, and there's 4 of them. So that means that there's a total of a -8. In order for this entire thing to add up to the -1 we have here, the manganese has to have a +7 charge, or a +7 oxidation number. Remember, charge, oxidation number are the same thing. Go from 7 to 2, I need to gain 5 electrons. So that way my charges balance out. +7 minus 5 gives me +2. So right off the bat, I found it. I found the metal that was going from a larger positive to a smaller positive number. Manganese is the species that is reduced as the oxidation number goes from +7 to +2, indicating a gain, because reduction is gain, of 5 electrons. Question B asks, the student used a 50 milliliter burette to add the KMNO4 to the oxalic acid until a faint lavender color was observed in the flask, an indication that the end point of the titration had been reached. The initial and final volume readings of the solution in the burette are shown below. Write down the initial reading and the final reading and use them to determine the volume KMNO4 that was added during the titration. So, all we need to do is look between the lines. If we look at the first right here, this 3, and count down, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 lines between 3 and 4, which means that it would be 0.1 per line. So it's 3.1, 3.2, 3.3, and it's halfway between, so we'd say 3.35 for the initial reading. The final reading, again, go through the process, 29.1, 0.2, 0.3, 0.4, 0.5, and again, halfway between 29.55 will be your final reading. So the difference between the two of them is 29.55 minus 3.35 is 26.20. That's your answer, 26.20 milliliters. But let's talk about some key points there. First, notice how I went from the top down because burettes count down. 0 is at the top, 50 is at the bottom, so it would be 1 milliliter, 2 milliliters, so on. Secondly, I'm measuring from the bottom of the curve, the bottom of the meniscus. That is where you always measure from on a burette. Don't forget that. Third, whenever I'm between, I always go to a half. Unless you're spot on the line, don't call it spot on the line. Use your best judgment. That is the uncertainty in your sig figs as far as you're allowed to be uncertain. You can go 1 decimal past what you're certain about, not 2, not 3, 1 decimal. Okay? 3.3, and then it's somewhere between the two of them. You can say 3.35, 3.36, somewhere in between. Third, I did 29.55, which has 4 sig figs, minus 3.35, which has 3 sig figs. But because I'm subtracting, it's based on how many decimals you had, not how many sig figs you have. And you go to the fewest amount of decimals. So 3.35 has 2 decimals. 29.55 has 2 decimals. They both have 2 decimals, so you'd round to 2 decimals no matter what your number is. Keep your rules for subtraction and multiplication and division of sig figs separate. So, C asks, given the concentration of KMNO4 was 0.0235 molar, calculate the number of moles MnO4 island that completely reacted with the H2CO4. Again, this is one of those questions where they give you extra information and try to trip you up, but really what you need to do is focus on the basics and the essentials, not anything else. Don't go the extra mile. It's asking how many moles MnO4 you added or completely reacted. That's all it wants. It just wants how many moles. So all you need to take is your answer from B, how many milliliters you got, convert it to liters, and that'll tell you how many moles, because molarity equals moles over volume, or moles equals molarity times volume. That's all you need to do. We have the molarity. We already found the number of liters. Don't overthink this. This is just the 0.0235 molar times the 0.02620 milliliters liters we found. Notice I converted from milliliters to liters because molarity is always measured in liters. It's the one conversion, the one trick you need to do. But once you do that, it just multiplies. And you get an answer of 0.0001230. Yep, just making sure I got that right. 616 moles. Don't overthink it. Don't overdo it. If you want to be in scientific notation, that'd be 6.16 times 10 to the negative 4th moles. And that's it. Again, be very careful you don't overthink it. And D, students asking to do this trial again, but this time they're going to use a lower concentration, a lower molarity of the KMNO4. Would this be a good choice, yes or no? This is a little tricky question. It requires you to think about experimental procedures, what's going on. So let's compare them. In trial 1, we used 0.0235 molar KMnO4, and then ended up using about 26.20 milliliters. That's a reasonable number of KMnO4 in a 50 milliliter burette. You're not going to run it all the way through, but you're not going to be too close to the top. You get a good degree of precision. The next trial, they want to not only move over, add an extra zero in front, they want to go down. This is roughly, quick, easy math, going from 0.02 to 0.001, 1/20th of the amount, which means you're going to need 20 times, 20x the milliliters. 20 times 26, rough, bad math, puts that over 400. 20 times 20 is 400. We'd need 400 milliliters, which means we need to go through a burette at least 8, and honestly more because we're doing rough and bad math, times. That's forever. You're going to go insane. Don't do that to yourself. This is a bad setup because the molarity of the KMnO4 is so dilute, you need to use so much of it that you wouldn't be able to do this in a reasonable amount of time or really understand what's going on. Bad procedure, bad idea, bad choice.